Now, I have discussed the rolling in last lecture. Now, let me take a question. Let me take a problem on rolling. Very simple problem I'll take. Suppose your wheel, you have a sphere. Say you have a sphere kept on the surface. Sphere, if I don't say anything, you assume it to be a solid sphere, right? If I don't say anything, by default you take it as a solid sphere, right? And suppose I hit the sphere, say along the center. I hit it along the center like this, along the line passing through center, giving it an instantaneous velocity of say v0. I give it an instantaneous velocity v0. Now I ask you a very simple question, that what is the velocity of the center of mass when the sphere starts pure rolling? I repeat the question. I hit the sphere along the center, which gives it a velocity of v0. Since I am hitting it along the center, this hitting will only lead to VCM, it won't lead to omega, because this hitting, while hitting, I am not creating any torque. Since I am hitting it along the center, I am applying a force along the center, so that's not going to create a torque. So at t equal to 0, your VCM is v0 and omega is 0. So what will happen? Your VCM is, I'll remove this point. So now we have this initial condition. So the point of contact, say P, what's the velocity at the point of contact? It's going to be v0 in this direction without omega. So point of contact is slipping in forward direction. Point of contact slips in forward direction. So in that case, what will be the direction of friction? Friction will act in backward direction. And when friction acts in backward direction, it leads to an acceleration of say A in backward direction. In backward direction. So that will lead to decrease in VCM. So that is v0 minus f by m into t. v0 minus f by m into t. And this f is also going to create a torque, Fr, and that will be I alpha, and I is, I'll take it as solid sphere. If nothing is told, you always take it as solid sphere. If it is hollow, they will write it. They will give you in the question, this hollow sphere. So what is alpha? Alpha is 5f by 2mr. And hence, I can say this alpha will lead to omega in this direction. This omega at time t is going to be 0 plus alpha t. Since omega in the beginning is 0, this is going to be 5ft by 2 omega r. So we are finding that your VCM is v0 minus f by mt, and you can say omega tr is 5ft by 2m. So your omega tr is increasing and VCM is falling. So a time will come, initially your VCM was v0, omega t was 0, omega r was 0. But as the time passes on, VCM falls and omega r increases. So a time will come when VCM will become equal to omega r, and what's that time? Let's see that time. v0 minus equals to 5ft by 2m, or this is 7ft by 2m. So time at which VCM becomes equal to omega r is 2m V naught by 7f. 2m V naught by 7f. So this is the time at which VCM will become equal to omega r, or this is time at which the rolling starts. This is time at which the rolling starts, and at when it starts rolling, your VCM comes out to be V naught minus F by mt. So V naught minus, and T is 2m V naught by 7f. So that's going to become 5 V naught by 7. 5 V naught by 7. Okay. So 5 V naught by 7 is the velocity when the surface, the solid starts, the sphere starts pure rolling. And of course, omega is going to be VCM by R, or you can just put it over here, the value that will be 5b by 7r. 5 V naught by 7r. That's going to be omega. This is VCM. This is going to be omega. Now the good question is, when it starts pure rolling, when the body starts pure rolling, what happens to the friction? What happens to the friction when the body starts pure rolling? Suppose I have the body here. When the body starts pure rolling, what is the velocity at the point of contact? In this case, the velocity at the point of contact becomes 0, or the point of contact comes at instantaneous rest. So what should happen to friction? F. See, the friction acts only when either there is a tendency relative motion at this point, or there is actual relative motion at this point. So in this case, when it starts rolling, I don't find any tendency relative motion because no force is acting. So why there should be tendency relative motion? I don't find any kind of tendency relative motion, and neither there is a relative motion because point of contact is at instantaneous rest. Whichever point is point of contact, that is at instantaneous rest. So there is neither a tendency relative motion nor there is actual relative motion. So the friction should become 0. There should not be any friction. Friction should not act at this point. Though the surface may be rough, but still friction won't apply, because friction apply only when there is either tendency relative motion or there is an actual relative motion, and you don't have both. You don't have any of the two, right? So friction force F acting on the wheel is 0, acting on the sphere is 0. So it means that we need this friction to begin rolling. If there is no friction, the rolling won't begin. The body will continue to slip with VCM equal to V naught and omega equal to 0. It's only because of friction that the body has started pure rolling. But it's also true that once it starts pure rolling, friction is not required to sustain rolling. When I'm saying all this, I'm saying only for this case. It's not in general true. It's not true for every example, in fact. Right? I'll take the next example and then you'll see that even when it starts rolling, friction will act. But in this case, friction won't act, because here this depends on the case-to-case basis. Like in this case, there is no tendency relative motion, neither there is actual relative motion. So why should friction act? So when we are talking about rolling on a plane surface, then we find that friction is required to begin a rolling. But once the sphere starts rolling, once the wheel or sphere or cylinder starts rolling, friction is not required to sustain a rolling. We don't need a friction to sustain a rolling. Means if the surface beyond this is the velocity this is 5 V naught by 7. It means when it starts rolling, even if the surface after this is perfectly smooth, the sphere can continue to roll with VCM equal to omega r if the surface after this point of time is smooth even. Because friction is not required to sustain rolling. Friction is not acting, so it does not depend on the surface. So friction is not acting, so it can even, once it starts rolling, it can continue to roll even on a smooth surface. Even on a smooth surface. So now the big question is, will it stop? Will it stop at any point, or it will continue to move forever? Will it stop, or it will continue to move forever? If it continues to move forever, that's a good thing. We can make use of it. Actually, it is not. Actually, it won't move forever. Here, the time has come to discuss with you about something about rolling friction. Rolling friction. Rolling friction. What is rolling friction? In fact, it's a different kind of friction. A new kind of friction will act over here, and that's the rolling friction. That is called rolling friction. From where comes this rolling friction? See, I'll give an example. So I'm now here to discuss rolling friction. See, when you push any object, suppose I have a wall over here and I have a person, suppose he is pushing the wall. When he pushes the wall gets depressed, the wall gets deformed. Every object will get deformed if I apply force on it. If I apply force on any object, the object is bound to get deformed. Howsoever hard it may be, the object will get deformed. If I push any object, if the person is standing, the surface will get deformed. It may be a case that this deformation won't be visible to you because the magnitude of deformation is too small, that it is beyond your range. It can't be seen by the naked eye or even with some less powerful microscope. But deformation is there. When you push any ground, when you compress, when you apply force on any object, howsoever hard it may be glass, it may be diamond also, but there will be some deformation. Maybe small, maybe negligibly small, but there will be some deformation. There will always be some deformation when you press something, right? Deformation will be there. Maybe deformation in nanoscale, micro scale, you are not able to see it. Does not mean deformation is not there. What we are not able to see does not mean that is not happening. It's not like that. The deformation is so small that it may not be visible by a naked eye or simple microscope, but deformation is always there when you push or when you compress or when you apply force on the object. And same is true for the wheel also. Like if I have a wheel and then I have a surface like this, the wheel is bound to get deformed. Wheel will get deformed at this point. You can see this point. The wheel will get deformed, and when the wheel gets deformed, the point of contact no longer remains a point of contact. It becomes a plane of contact. When the wheel or the sphere gets deformed, the point of contact is not single one. It's succession of the point of contact. You have many point of contact. Or I can say for a sphere, it becomes a plane of contact. Or for a wheel, it is line of contact now. But if it is a wheel, if it is a disc, it is a line of contact. Or it won't be a single point of contact. That's what we mean to say, because you have a normal reaction acting at this point and the wheel apply a normal reaction on the ground in downward direction. This force of interaction, the wheel is bound to get deformed. The wheel is bound to get deformed. And now when you have this plane of contact, what is happening is, when wheel is moving in this direction, it's pressing this point harder, and this point is about to get lifted. Point A is getting pressed and point B is about to get lifted. It will press the wheel in direction of A. It will press the wheel in this direction, and this part is going to get lifted up. So since you are pressing this A, the normal reaction at this point, A is going to be slightly higher. Say normal reaction is this. This is going to be the normal reaction, right? And the normal reaction B will be smaller. Normal reaction B is going to be smaller. So if this is normal reaction N1 and this is normal reaction N2, so in this case this is N1 and N2, so I can say that N1 is greater than N2. N1 is greater than N2, and then I can draw a dotted line over here. Say the magnitude of deformation will be defined. Say this is an angle of, say, d theta. So this d theta, how much will be this d theta, will depend on this deformation. If deformation is large, this angle will be large. So assuming the deformation to be small, this is going to be your d theta by 2, and this angle is also going to be d theta by 2. And since there is a mismatch in N1 and N2, see, the vertical component of N1 and N2 is not going to affect the horizontal motion. So in the horizontal direction, you are in this direction, the net force, the horizontal component of N1 is going to be N1 sine d theta by 2, and horizontal component of N2 is, and the lie in opposite direction. N1 sine d theta by 2 and N2 sine d theta by 2 is lying in opposite direction. So you have this force on the wheel which act in backward direction. You have this much of force acting in backward direction. So your net force on the wheel acting in backward direction, and this is what we call as rolling friction, approximately d theta by 2. So this mismatch of N1 and N2, which arises because you have now a plane of contact due to deformation, and this is what we call rolling friction. This is called rolling friction, and this force will slowly reduce the velocity, and ultimately the wheel or the sphere comes at rest. So this rolling friction is responsible for bringing the rigid body, the cylinder or the disc or the sphere, to rest finally. But this force is very small compared to the other kind of friction like dynamic friction. This is very small compared to dynamic friction, and it has dependence on the deformation. Like in case of trains, the wheel is made of steel, iron. In that case, deformation is very, very small. When deformation is very, very small, then rolling friction is very, very small. So if you reach a very high velocity in case of train and put off your engine, then train is going to move over a very, very long distance. So usually in express train, what is done is you reach a very high velocity and then you can't put off the engine and continue with the same velocity, right? So that phase is called coasting. In case of traction engineering, that's called coasting. The train is in coasting phase. The velocity do not change. The velocity do not increase or decreases. The train is moving with constant velocity. So that is possible. That is a good way of saving a fuel. Because deformation is very small, rolling friction is going to be very small. So the train can undergo a coasting phase where the velocity will be maintained very constant and can move for a very long distance without burning any fuel, right? So that's how the rolling takes place. Okay, thank you very much.